Today, we are breaking down a 2017 research paper that, and I'm not exaggerating here, became the blueprint for modern AI. A paper that didn't just inch things forward, it completely rewrote the rulebook for how machines could understand language.
So, to really get why this was such a revolution, you first have to understand the huge problem that AI had with language. It's all about context. Take this sentence. The bee landed on the flower because it had nectar. Now, for you and me, it's obvious. It is the flower. But for an AI back then, making that connection, linking it all the way back to flower was a massive, massive challenge. This one problem, understanding these long-distance relationships in text, was basically holding back the entire field.
So here's how we're going to unpack this. First, we'll look at the roadblock that was throttling progress. Then the incredible breakthrough that just shattered it. We'll dive into the mechanics of how this new model actually works, look at the jaw-dropping results it produced, and finally, talk about the massive legacy it's created. All right, let's get into it.
Okay, so first, let's set the scene. Before 2017, the AI models that dominated the field were really clever, but they all shared this one fundamental, speed-limiting flaw in their design.
The big players were called recurrent neural networks, or RNNs, and they worked by processing sentences sequentially, word by word by word. Imagine trying to read a whole book by looking through a tiny little tube, seeing only one word at a time. That's pretty much what they were doing. The paper calls this an inherently sequential nature, and it meant they were slow, they were difficult to train, and, this is the kicker, they would often forget what the beginning of a sentence was about by the time they got to the end.
This table from the paper just lays the problem out perfectly. Look at that top row for the old RNN models. The number of steps it had to take grew with the length of the sentence. That's the O of N. Longer sentence, longer and longer process. But with this new idea, self-attention, it's a constant number of operations, O of 1. It doesn't matter how long the sentence is. The path between any two words is always direct. For speed, for context, this was a total game changer.
So this huge roadblock, this sequential problem, really set the stage for a completely new way of thinking. The authors over at Google didn't just want to kind of improve the old way. They wanted to throw it out completely.
And this sentence, right here, is the heart of the whole paper. Their solution was so radical, but also so elegant. Just get rid of the one word at a time processing. No more of that sequential stuff. No more recurrence. Instead, they would build a brand new architecture called the transformer, based entirely on this one mechanism called attention.
And this is the magic trick that makes it all possible, self-attention. What it does is it lets the model look at the entire sentence all at once. So to understand the word it can directly compare it to bee and flower at the exact same time and figure out which one is more important. It models all these connections, as the paper says, without regard to their distance. That tiny tube is gone, and it's been replaced with this incredible panoramic view of the whole sentence.
So how does this new architecture actually function? What are the nuts and bolts of a model that can see an entire sentence at once? Okay, let's pop the hood and take a look inside.
All right, so from a bird's eye view, the transformer uses a pretty classic setup, an encoder and a decoder. The encoder's job is basically to read and really understand the input sentence. It chews on it and creates this rich numerical representation that's just packed with context. Then, the decoder takes that rich understanding and uses it to generate the output, like a translated sentence. But it's what happens inside those two boxes that's so revolutionary.
Diving a little deeper, what the paper lays out is that both the encoder and the decoder are actually stacks of 6 identical layers, one on top of the other. And while each layer has a couple of parts, the absolute core engine, the real star of the show, is that multi-head self-attention mechanism. That's where all the magic is happening.
And this part is just brilliant. Instead of having just one general attention mechanism looking at the sentence, they split it into 8 heads, at least in the base model. Think of it like this. Each head is a specialist. One might be looking for grammatical structure. Another might focus on who's doing what to whom. The paper says this lets the model jointly attend to information from different representation subspaces. It's like having a whole committee of experts analyze a sentence instead of just one person.
But wait a second. If you get rid of processing things in order, how on earth does the model know the order of the words, right? The dog bit the man is very different from the man bit the dog.
Well, the solution is something called positional encodings. It's so clever. Before anything else happens, the model adds a little bit of information, like a digital zip code, to each word that basically tells it its position. It's done with a really cool mix of sine and cosine waves, and it injects that vital information about word order back into the system.
Okay, so a beautiful theory is one thing, but in the super competitive world of AI research, results are everything. And the Transformers results, they weren't just good, they were absolutely stunning. And this just says it all. So on a standard translation test from English to German, the very best systems at the time, and these were complicated systems, ensembles of multiple models, they scored around a 26.4. The big transformer model, 28.4. Now, a 2-point jump in this world is a massive, massive leap. It just established a completely new state-of-the-art.
And it gets even better. On another task, English to French, the transformer set a new record while using less than a quarter of the training cost, the raw computing power, of the previous best model. This right here was the devastating 1-2 punch that changed the entire field. The transformer wasn't just better, it was also fundamentally faster and cheaper to train because you could run all these calculations in parallel. It completely broke the old trade-off. You could now have much higher quality for less cost and in less time. That's a true paradigm shift.
So the ripples from this paper went way, way beyond just machine translation. It handed the world a totally new blueprint for building language models, and it sparked the AI revolution that we are all living through right now.
So when you boil it all down, what's the ultimate takeaway here? The paper's real contribution wasn't just a better translation model. No, it gave the world a new, powerful, and incredibly scalable building block. It solved the parallel processing problem, it cracked that long-range context issue, it delivered top-tier performance, and in doing all of that, it laid the foundation for almost every single major large language model that came after it.
You know, from ChatGPT to all the countless other generative AI tools we use every single day, the architecture deep down at their core is the transformer. The principles from this one paper in 2017 are now just everywhere. They're a fundamental part of our technology. Which really leaves us with one final provocative question. Looking at everything that's been built on this foundation since, were they right? Is attention truly all you need?